Hello, and welcome to this Institute of Physics CPD session on Newton's third law. This is the first in a series of videos on Newton's laws, and you'll notice that we've decided to present them in reverse order. In our experience, we've found that it's useful to really cement those ideas around interaction pairs, which we discussed with Newton's third law, before going on to discuss ideas more related to motion that we find in Newton's second and first law. Of course, we'd encourage you to reflect on your own sequence of teaching for Newton's laws and think about what would work best for your students. Let's begin. Okay, so we're going to start off with a question that comes from the 2015 A-level series, and it's quite similar to this one. It starts with an object on a surface. We have the downwards force labelled, we have the upwards force labelled, and when talking about the diagram, we have a statement which is along the lines of a student saying, this is an example of Newton's third law, and then to explain why that statement is wrong. I'd encourage you just to pause the video here for a moment and just have a bit of a reflection on what your students might say in response to this question, and perhaps any other thoughts you might have on the question or the diagram itself. Okay. So I don't mind admitting here that a handful of my students came out of the exam saying, Miss, there was a mistake on question 1. It said explain why they were wrong about Newton's third law, and it should have said explain why they were right. And when I had the opportunity to go and have a look at the question, it dawned on me that this sort of small group of students hadn't really understood what was meant by Newton's third law. And we'll unpick, over the course of this video, one, why they were wrong, but also approaches that we might be able to take to help them, overcome their sort of lack of understanding about Newton's third law. I also asked you to think about the diagram as well, and in one of our other videos where we talk about representing forces with arrows, one of the things we discuss is the constraints that exam boards can have because they have to print everything in black and white. So you'll notice that because they're keen, as we should be as physicists, to show the forces acting at the point of application or at the centre of mass, those two force arrows overlap each other, and that can make our diagram look a little bit cluttered. So one of the things that we might try and do here is actually encourage our students to draw two separate diagrams for the two forces, and then really to think about those forces that are acting to help sort of conceptualize what's going on in the picture, and hopefully make it a bit more manageable for them. But let's have a look at where some confusion has come from in this question and try and unpick some of the reasons why. So the first thing we perhaps need to do is look at what Newton's third law actually says. It goes along the lines of, if object A exerts a force on object B, then object B will exert an equal and opposite force on object A. Now, I anticipate that some of you might be looking at this and thinking, oh, I've not heard Newton's third law expressed that way. And it's probably quite likely that you'll have heard of it referred to in this way instead. This really short-handed, snappy, dead easy to write in the book. For every action, there is an equal and opposite reaction. And in the case of my students, this is what they'd gone into the exam thinking. They'd sort of revised that for every action, there's an equal and opposite reaction. They'd seen that those upwards and downwards forces were equal in magnitude, acting in opposite directions. They've applied this law and sort of come up with, unfortunately, the wrong conclusion. Because we've missed, in shorthanding this law, we've missed that extra information they needed, object A and object B, and it meant they weren't thinking in terms of object A and object B. One of the other things this statement misses is the fact that the type of force has to be the same as well. And so, shorthanding laws in this way can cause some of these issues because students just don't have the information that they need. It doesn't just apply to Newton's third law either. It can apply to other types of law, such as Ohm's law, for instance. Ohm's law, quite often we can find that students just talk about that proportional relationship between potential difference and current. and it kind of misses out that really important element, which is that only applies when we have a constant temperature sort of situation. So we need to be really careful when we're talking to students about laws. And even though, yes, we want a really shorthand, snappy way of remembering it, but we need to make sure that students are aware of all the information in the laws before we try and shorthand these laws down. So let's go back to our question again with the rocket and think about one of the issues that's arise with this action and reaction interpretation of the law. So clearly what's happened is that our students in this case have mistaken the reaction. We've discussed the idea that the forces are equal in size, they're opposite in direction, and we've mistaken what the reaction is. And that's quite common for our students to do. So if we go back to our fuller law, as it were, if object A exerts a force on object B will exert an equal and opposite force on object A. Well, hopefully one of the things we can see quite clearly is that this can't be a situation of Newton's third law because both the forces are acting on the same body. Okay, so in this case, that downwards force and the upwards force, they're both acting on the rocket. There is no object A and there is no object B. The second thing, we sort of discussed it earlier, is that the types of forces are different. So that downwards force is being caused by the gravitational force of the Earth. The upwards force is being caused by, by the bench, essentially, that's supporting the rocket. So this is where force sentences, again, that we've met in a different video, can really help in this type of situation, where we're getting students to think about what kind of force we've got, what's providing the force, and what the force is acting on. We do that in order to be able to complete the phrase like the one below. So if we go back to our rocket again, and in this case we just focus on that downwards force, okay, we can see now, if we can complete our force sentence, that we've got the gravitational force of the Earth on the rocket. And why these force sentences are really useful in a Newton's third law situation is that if we want to identify the interaction pair, we quite simply just swap those last two terms around. So if we do that in this situation, we can see now that we have the gravitational force of the rocket on the Earth. And what we've got is a situation where we've got object A, which is the rocket, we've got object B, which is the Earth, and the type of force, that gravitational force, is the same in both situations. And of course, let's not forget that those forces should be equal in magnitude as well and acting in opposite directions. If we look at another example now, we're going to look at a situation where we've got a pair of contact forces. And to do that, we're quite simply going to use the situation of a hockey stick pushing a ball. So using our force sentences again, we've got the push force of the hockey stick on the ball, and switching those two terms around, we can see that the interaction pair is the push force of the ball on the hockey stick. One of the things that you'll have probably noticed as well is that where I've represented these forces in diagrams, I've made sure that the type of force is the same colour. And I'd encourage you to do that with your students as well, because assigning different colours to different types of forces can make it really, really clear where there's an interaction pair. Because where you've got two colours which are the same, you can sort of really clearly see that it's the same type of force. So in this situation, we've got the forces are acting on different bodies. So object A could be the hockey stick, object B could be the ball, or vice versa, depending on how you want to assign them. And the type of force is the same. It's that push coming from the hockey stick. Now, we've got the idea then that we've got this interaction pair, and forces do always act in pairs, but because of this, and if we've misunderstood Newton's third law, we end up in a situation where students will try and force pairs into a situation. So if we think about our hockey stick and ball example again, and we're going to think about the forces acting on the ball just as the ball has been hit. So it's been hit, it's left the hockey stick, and it's starting to make its motion across the pitch. So encouraging our students just to think about those forces acting on the ball. Most of them will recognise that there are going to be resistive forces at play. So there'll be the friction of the ground, there'll be the air resistance of the ball, and those forces will be acting in the opposite direction to the motion of the ball. But because our students are so keen to show that there's a pair acting here, because they've got that forces always acting in pairs rule in their head, they will then put that forward force, basically what we know is the motion of the ball, but they'll put it as a force acting forwards as well, and they'll label it on the diagram like this. Again, I just encourage you to pause the video here and to get you to think about that if a student presented this type of diagram in their book, or if they were talking it through with you, what might you do to get them to improve their diagram and get more of the correct physics on the page or in their conversations. So this is another example of where our force sentences can be really useful. So one of the things I would do with my students is now ask them this series of questions again to get them to think about what's actually happening in the situation. So in the case of that forwards sort of blue arrow now, I would get them to say, well, what kind of force is it? And they would say, well, it's that push force. It's the force that's making the ball go forwards. And I say, okay, well, what's providing the force? So we'll go down into that second question. And I'd anticipate that they probably say, oh, the hockey stick is providing the force. And then we sort of delve into that a little bit deeper and sort of say, okay, but the ball has left the hockey stick. So can the hockey stick still be providing that force? And hopefully they'll say, oh, no, well, it can't be. And so we say, well, is there actually a force there then that's being provided by the hockey stick? And they say, oh, well, no, there's not. And hopefully what that then does is enable them to see that that blue arrow, that forwards arrow they've put on, is not there. So when we come to redraw our example again, we're hopefully ensuring that that blue arrow isn't there. And what we've instead got is a green arrow representing those resistive forces. Now, one of the other things you might have picked up on here is that in redrawing this diagram, I've moved that green arrow from acting at the center of the ball, and I've put it towards the bottom instead. And again, this is a conversation we want to have with our students, where we're talking about getting them to represent the forces where they're acting. So in this case, the biggest resistive force we're going to have is going to be friction along the floor. So I've drawn my arrow now at the point where the ball would be in contact with the ground to really show that that's where my resistive force is happening. So what we want to encourage our students to do is to work through this line of questioning to give an example here where we've just got the one force acting on the ball, and that's okay, especially in that horizontal plane, and to show that it's acting at the point where the ball is in contact with the ground. Brings us on to our last issue that students sometimes have with Newton's third law, if they're starting to really now think about it more deeply. And that is, why don't these action and reaction pairs cancel out? So again here, when we're thinking about developing a forces model, we're encouraging them to isolate the ball and just think about those forces that are acting on our ball. And if we do that, then we can see that just as the hockey ball is being hit, the only force that's acting on it is that forwards force pushing the ball forwards. And we can see here now that because there's just that one force, we have an overall resultant force which is going to cause our ball to accelerate forwards. So, in summary, here are some things that we would encourage you to do with Newton's third law. The first is to mind your language. Try and avoid shortening down the laws straight away. Make sure when you're having the conversations about this law or any law to do with physics that you are including all the information in that discussion before you start to shorthand things down. The second is to make use of colour when you're drawing your force arrows, or if you use cardboard arrows or sort of anything like that. Try and encourage the same types of colours to be used for the same types of forces. This way, when you've got your diagram, if you can show that those two colours are the same, then it makes it really obvious that you've got the same type of force. The third thing is to use the questions that we've suggested to construct these force sentences. So get students all the time to be thinking about what kind of force is it, what's providing the force, and what is the force acting on. And then finally, we would encourage you to get your students to use this Newton's third law checklist. So both the forces are acting on different bodies, we've got the object A and object B, the type of force is the same, and the forces have the same magnitude and opposite direction. Thank you, and I hope you've enjoyed this Institute of Physics CPD session on Newton's third law. Please do join us for the other 2 videos in this series, as well as other Institute of Physics CPD sessions on offer across a broad range of topics. Goodbye.